Welcome! In this session we contrast centralized plants with package systems and connect condenser selection and cooling towers to system design. We also outline how energy management and cooling control systems supervise local loops and maintain comfort and indoor air quality efficiently. The aim is to support early-stage selection that remains coherent with sound design and airside decisions. The content of this video, we begin with the architecture of centralized plants. Then we review package systems and their integrated nature. Next, we compare condenser options and when a tower is appropriate. Then we summarize what are energy management control systems. Next, we give some implications and selection cues, and finally we mention common pitfalls in these systems. By the end of this video, you should be able to state the principal difference between centralized and packaged approaches and where each tends to fit. You should recognize which systems require cooling towers and the implication of that choice. And you should explain how EMCS supervises local control loops to meet comfort and indoor quality with attention to energy. But let's start with the question. I want to ask you to picture a typical afternoon, an office that's half empty, a packed meeting room, and a copy print room with equipment running, all on the same floor. Each space has different heat and moisture loads and different people counts, so they don't need the same supply. As you think, compare three simple approaches. Give the same air to every room, give different amounts of air at the same temperature, or give different supply temperatures, or a mix of warm and cool air. Two different rooms. Which approach seems most likely to keep comfort and air quality steady most of the time? Now test your choice. If every room always gets the same airflow, the meeting room will likely feel stuffy and warm. The open office may feel too cold, and the print room can drift hot from equipment gains. You may also miss the outdoor air person target in busy rooms. Most buildings spend many hours at parallel load, so the winning strategy is the one that can adjust as occupancy and internal gains change through the day. Keep the reasoning in mind as we learn the formal system types and control that implement these ideas. A centralized HVAC system is a building-wide heating, ventilation and air conditioning system where the main equipment, such as chillers and boilers, is located in a central plant, separate from the air handling units that condition the air for individual zones. This setup allows the system to serve multiple zones and buildings through a network of chill and hot water distribution lines. In centralized designs, air handling units and heat generation reaction are separated. Air handler units serve zones while chillers and boilers deliver chill and hot water to coils. Centralization enables coordinated control, maintenance, access, and opportunities for plant-level efficiency improvements. This often aligns with buildings that have many zones and significant diversity across operating hours. In contrast to centralized plants, package or unitary systems are self-contained, integrating all major components like compressors, coils, and fans into a single compact unit. This design simplifies installation and offers a straightforward local control, making them a popular choice for smaller to medium-sized applications. Package systems integrate refrigeration and air handling into rooftop or wall-mounted units, simplifying deployment. Their controls are straightforward, favoring smaller projects or where central plant infrastructure is not available or viable. Heat is commonly rejected to ambient air through an air-cooled condenser in these configurations. We have just reviewed how different HVAC architectures handle heat rejection, particularly in the context of packaged units. Now let's take a closer look at the two primary methods for heat rejection, air-cooled and water-cooled, and examine the role of cooling towers, a critical component in larger water-cooled systems. Air-cooled condensers are typically of packaged systems and smaller plants. Water-cooled condensers require a condenser water loop and a cooling tower for heat rejection, common in larger central plants. Towers and add auxiliary systems, water supply and treatment, and require control of tower fans and basing conditions to achieve target approach temperatures. Now that we have looked at the main components of HVAC systems, let's explore how a central nervous system ties them all together. The Energy Management and Control System, EMCS, acts as the brain of a building HVAC operations, moving beyond simple local controls to achieve overall efficiency and performance. While each individual piece of equipment has its own local control loop, the EMCS is a supervisory system that orchestrates their actions, ensuring the entire system works together seamlessly to meet comfort and indoor quality requirements. So each subsystem includes a local control loop, valves for coils, speed or variable frequency drives, VFDs, for fans, dampers or local fans in terminals. The EMCS supervises the loops with strategies such as supply air or chill water temperature resets, plant and air handler units scheduling, and economizer enabled where applicable. Supervisory monitoring supports fault response and maintainability while preserving comfort and indoor air quality requirements. Then we have the application. After examining the individual components of HVAC systems, we will now synthesize that knowledge by looking at how to select the right system for a given application. Select the architecture that matches building scale and some complexity. Central plants justify their infrastructure when coordination yields benefits. Package systems remain appropriate where simplicity and independent local control dominate. The condenser and tower choice follows from capacity and efficiency targets, weighed against water and maintenance requirements. Now we'll turn our attention to the potential pitfalls that can arise in the design and operation of central and packaged systems. Terminal selections impact central fan energy. Induction devices require explicit static allowance. Cooling towers demand planning for makeup water and treatment to sustain heat rejection performance. Without supervisory resets and scheduling, systems may consume unnecessary reheat and fan power at part load. Let's finish this lesson with some key takeaways. Your choice between a centralized and a packaged system comes down to a fundamental trade-off. Central plants offer greater potential for optimization, control, and efficiency, but they require significant infrastructure. Packaged systems, in contrast, prioritize simplicity and localized control. When considering water-cooled condensers, be aware that they are not a standalone solution. Their use implies the need for cooling towers and the associated maintenance, including managing water quality and treatment, as well as budgeting for their operational commitments. Finally, remember that an EMCS is essential for bringing it all together. It adds a significant value by coordinating the various local control loops, such as fans and valves, through setpoint resets and schedules. This ensures that the system meets comfort and indoor air quality requirements efficiently, and especially during the many hours of part load operation. Now I invite you to continue learning. You can explore demand control ventilation. It adjusts outdoor air to real occupancy using CO2 or people count signals, so a crowded meeting room receives more fresh air while a half-empty office isn't overventilated. Look into temperature and pressure reset strategies, raising supply air or shear water temperatures and lowering deck static at part load to cut reheat and fan energy while keeping comfort steady. And check out fault detection and diagnostics, using EMCS train data to spot stock dampers, drifting sensors, or short cycle equipment before complaints and waste energy show up. These concepts turn simple choices into smart, responsive systems and open up many practical ways to improve comfort, indoor quality, and efficiency. Thank you for watching this video.